Okay, we're going to start with this beam. This is a cantilever with the fixed end on the right and free end on the left. You can see we have a point load and a distributed load. So I want you to start by taking a couple minutes, so maybe take 2 minutes, and see if you can draw the shear and moment diagram for this. Okay, so as you can see, the shear diagram. Starts by going down. I ran the wrong slide. Starts by going down. Then we go across to the midpoint, and then we have a linear segment coming down. So with a little bit more experience, you should be able to draw this shape about as fast as I just drew it there. You shouldn't have to think about this. You need to practice shear and moment diagrams until they become so second nature that you can do them impulsive, or I don't know, what's a good word? Instinctively, right? You should know that when you see a point load, your shear diagram is going to move in that direction vertically. When there's no loading, so in this region where there's no loading, you should know that you're going to have a horizontal segment. You should instinctively see this uniform load and say, okay, the integral of that is going to be linear. So I'm going to have a linear segment, and it's going to go in the direction that that load is going. And then at the end, I'm going to have some kind of vertical reaction that's going to close it. So you can get this shape without knowing any of the numbers. Then you come back in and you say, okay, well, this has to be 2 because that's how much my force is. This slope has to be 1.5 because that is what I have here. And so I can say that the change in shear is the integral of my loading. Is that familiar? So if I have this negative 1.25 kilonewtons per meter and I integrate that over 2 meters, I know I have a change in shear of 3, which means I go from -2 to -5. So that gives me this value of 5 here. Then anybody have the moment diagram? Okay. When I have let me back up. When I have my change in moment equals the integral of my shear. So when I start this moment diagram, I know that because I'm at a cantilevered end, the moment has to equal what? What's the moment at the end of a cantilever? That is the moment that a force at the end of a cantilever would cause some distance away. But what's the moment in a member at the end of a cantilever? Should be 0. Excellent. So I know this is going to start at 0. Okay. Now I know that I have a uniform or a constant shear. So what is the integral of a constant? If I have 5, what's the integral of 5? Okay, so what's the integral of a constant? The slope line, right? 5 becomes 5x, a constant becomes a constant times x. So I have -2, which means I'm now going to have a line with a slope of -2. So -2 slope acting over 2 meters takes me down to -4. Good. And you can also get that by taking the area under this curve, right? The integral is the same as the area under the curve. So this is a negative curve, therefore it's a negative area, which means I'm going down in my moment diagram. So I come to a -4. Now I have a linear segment of my linear segment of my shear diagram. So when I integrate a linear equation, I get a perfect quadratic. So this is going to become a quadratic equation. But rather than getting the equation itself, in this case, the easiest thing to do is to look at the area. So that area underneath the curve, this here, I can get the area of that, and it happens to be, I believe, let's see, -7. So that means I'm at -4 right now. I need to go down to -11. then presumably I'll have some moment at this end, some moment reaction that's going to have to close this. So one way to, in this particular problem, because your cantilever is coming from the right-hand end, you could start your diagrams on the left, move all the way to the right, and whatever you end up with has to be your reaction. Now, that's probably not a good way to do it. Shortcutting the solving of the reactions is probably not good advice, because if you made a mistake in your diagram somewhere, you're not going to catch that. So what you might want to do instead is start by taking the sum of the forces in the vertical direction equal to 0. So you calculate what this reaction has to be, this vertical reaction, and you're going to get that that reaction is 5. Therefore, when you come over here and you get 5 on your shear diagram, or rather -5, you know you've done it right because you're going to close to 0. Same thing with your moment diagram. You're going to solve for this moment, and this moment is going to be 11 kilonewton meters. Put that somewhere better. So you know when you end at that -11, you now go up to 0. When it comes to the moments, though, it's sometimes a little tricky to know whether this reaction is positive or negative, what it does to the beam. The way that I always like to think about it is, what would that moment do to a beam segment that is on the right side of it? So if for example, this beam were to continue over here, what effect would this have to that segment of the beam? So in order to do that, I imagine I just keep rotating this moment around this way until it makes a little bit more sense in my head. I'll put that in a better color. So I don't know about you, but for me, it makes a little bit more sense to think of the arrow as that blue arrow than the red one when I'm trying to think about what it's going to do to the right-hand side. And now that I've rotated it around, I say, oh, that's going to make it smile, right? If I pry this end up, I'm going to have a smiling beam. So that's a positive moment, which means my moment diagram has to become more positive than it was. So I'm at -11, I get more positive, closes to 0. Okay, that's how I think through it. One thing I want to point out that's highly problematic for people who are starting out shear and moment diagrams is, how do you know what this parabola looks like? Yes?
One way I remember is you're going to look at the line that you're seeing, and since it's distributed, it's going to accumulate force as you go along, so then your curve should reflect that. So it should start with a less steep curve, and it should accumulate as you go.
Good, that's great. So I think what you're saying is here, when we go a little bit of distance along the beam, we gain some small amount of change in moment.
Yeah.
Relative to over here, we go that same delta x. Now you're accumulating more change in moment. Good. And so here you can see this is somewhat, it's not flat, but it's more flat than say there. So your change in moment as you go towards the right, your shear is getting larger and larger, and so your slope should be getting larger and larger as well, right? If the moment is the integral of the shear, then the shear is the derivative of the moment. And so if you think about your derivative, you start out with a slope of -2, and you have to end with a slope of -5 in your moment diagram. Good. Any questions about that? Yes?
How can we tell if it's concave up or concave down?
Okay, so concave down is like this, concave up is like that. The way that you want to think about that is the slope, it goes back to this equation. The slope of that diagram has to match the shear. If these are negative values for your shear, you have to have negative slope. Both of these match the negative slope, right? But the difference is this one starts with a small negative slope and ends with a big negative slope. This one starts with a big negative slope, and this one ends with a small negative slope. What you want is you want to start with a small and end with a big. So that would correspond to that one. And specifically in this problem, that slope had better be -2 and that had better be -5. Now, when you're drawing it, I don't imagine that you're getting your slopes to scale. I know I never did as a student, but one should be steeper than the other. Good questions. Anything else? Okay. Let's look at this one. So we want a shear and a moment diagram for this one as well. I'll give you a couple minutes to think about it, and then I'll start getting into it. Okay, so when we talk about our shear diagram, in statics, we talked about how if you have a reaction or a point load, your shear diagram is going to move vertically in that direction by the same magnitude. Okay, so for this one, we're going to have reactions at A and B, correct? We'll have 2 vertical reactions. How do I get the magnitude of those reactions? Okay, the moment about A, the moment about B, and you get either one, and the 2 of them should sum up to that total load. In fact, I'll go one step further. 2/3 of your load should be resisted at B, 1/3 at A. We have that triangle, which means it's going to have a resultant right here. And because that resultant is 2/3 of the way across, it's going to put 2/3 here and 1/3 there. So we can get those reactions. Those reactions are 240 and 480. All right, so knowing that, where does our shear diagram start? Positive 240, good. Okay, that should be your very first thought. You always want to think to yourself, at this left-hand side where I'm beginning, is there a reaction? Is there a point load? What would the shear value be? If I'm at the end of a cantilever, the shear value should be 0, unless there's a point load there, in which case I follow that point load down or up. I saw a number of diagrams that started at 0 so on your papers. So please make sure that you always remember that if there's a reaction, you need to account for that in your shear diagram. Next, we have this loading. This loading is a linear load, which means our shear diagram will look like what? It'll be quadratic. Linear integrates to quadratic. Now, Dr. Nasri did a really good job picking out these problems, because what I like about it is this first problem you can do by inspection fairly easily. You know the shape, this general shape, I can get that without doing any math, and I can get this without doing any math. And then I can come back in and pick off a few values off of this table, or this image, for example. I can get this 2 kilonewtons. I can figure out this reaction. From those 2 pieces of information, I know what the magnitudes of my shear diagram are. Similarly, I can get the moment reaction, and I can just take a quick integral of this rectangular area to get my moment diagram. You can do the same thing here, right? You can integrate kind of geometrically, but it's not as easy. You know, none of us want to be adding up the area under a parabola, right? So I like that these are kind of 2 different approaches. This one, because we're dealing with higher orders of equations, would be easier to do by integration of the equation itself. So when I'm approaching this problem, I might be able to do a couple things. I might be able to say, okay, this is starting at 240 and it's ending at 480, because I know when I get to that end, I have to push it back up by that reaction 480. And then in between, I know it looks like a parabola. And I know that at the left-hand side, that parabola has a slope of 0, right? Because the W is equal to the derivative of our shear. If your shear is the integral of your load, then your load is the derivative of your shear. It goes both ways. So that means that I'm going to start out with a slope of 0, and I'm going to end with a slope of 120. That's going to be very steep. This is 0, and so it's going to look something like that. So I could do that. But now to get from this to my moment diagram by inspection is exceedingly difficult. So instead, what I'm going to do is I'm going to say that I need an equation for this loading. So I'll say this loading I know is negative because it's pointing downward. And when I'm at a distance of x equals 12, I want it to equal 120. And when I'm at a distance of x equals 0, I want it to equal 0. So that looks like a linear equation without a constant. So I just want the linear term. And if I take the magnitude of my loading divided by the location where I want it to equal that magnitude, and I stick an x on it, that is my equation. So plug in 0, plug in 12, confirm that you get this triangle. Does it look right? Okay, we're all in agreement that this describes that loading. So now if I want my change in shear, I can set that equal to the integral of that equation. So, or let me drop off the change in shear. My shear is going to be equal to the integral of that. So I have negative 120 x squared over 24 plus some constant. What do I want this to equal at 0? X equals 0? Plus 240? Or did you say something else? At x equals 0, what do I want my shear to equal? 240, plus 240. Okay, so that means this constant is 240. And now I can get the shear at any location between 0 and 12. And this is the equation of a parabola. And if I plotted that parabola, it would look pretty much like what I have drawn there, barring any not to scale. And I can then solve, very importantly, I can solve for where shear equals 0. I plug in a 0 for V, and I solve for X. And that gives me this value, which happens to be 6.9 feet. Okay. Then, if I want my moment equation, I know that's the integral of my shear. So we have negative 120 x cubed over 72 plus 240x plus what's my constant? The constant has to be the value of the moment when x equals 0. What kind of support do I have at A? Okay, let's try it a different way. What type of motion is prevented at point A? Vertical, horizontal, okay. Anything else? No. So it's the prevention of movement that causes a reaction, right? If I have nothing preventing this, there is no reaction. It's only when it hits the floor that there's a reaction on it, because the floor prevents the movement. So I have reactions in the X and the Y because I have motion prevented in those directions. But it does not appear that there's any prevention of rotation, correct? So if you're free to rotate, you don't develop moment. Your moment is 0 if you can rotate. It's only when I start preventing that rotation that I feel it in my wrist. Take your pencil, go like this. Loosen your hand and just move it freely. Do you feel anything in your fist hand? Maybe not much. Now tighten your fist hand and now try to move your pencil. Do you feel something kind of in your wrist? That's moment. You're preventing it by moving with moment. So moment is 0, therefore my constant is 0. If we had some kind of, say, cantilever at at 0 to where our fixed end was at 0, so we know there is a moment, but we don't know how much, then you would add this constant in. You would need to know your moment at some other value of x, and then you'd back solve for what that constant would be. But in our case, it's 0. So now we have this equation to plot. And we know that it's going to start at 0. Do we know anything else about this parabola? Sorry, it's not a parabola, it's a cubic equation. Do we know anything more about this cubic equation? What does this tell us? Let's not answer that question. I have a better question. What does this tell us? It is going to be concave down, and it's going to be increasing in value, right? It's going to be increasing in value. So what that means is it's going to increase as long as this area under the shear curve is positive, and then when it becomes negative, it will start decreasing. And because the slope of the moment is equal to the shear, we know that at this point, the slope is equal to 0. So I have some 0 slope here. This is going to start with a slope of positive 240. So slope of 240 going to 0. Now it's going to go from 0 to a negative 480. And where is it going to end up? Will I end up here, here, or here? Above, below, or at the axis? It has to end at 0. Thank you. It has to end at 0 because there's no moment reaction at B. So therefore, this has to come down like that. So it looks kind of like a lopsided parabola. And then you can get this value, this 1109, by plugging in 6.9 feet for x. Because we already know that's where the maximum occurs, so we plug in that x value and we get that. It's really important that you have some of these gut instincts about how your diagram should look. The numbers are great, but really this intuition about what it should look like is more important. Okay, and then the other thing I like to do, because when I draw things, because you're in an academic setting where we're grading you, I like to add this little note that says cubic, because my cubics tend to look just like my parabolas, and at least that way the instructor knows I know that it's a cubic equation. Also, keep in mind these cubics that we're drawing, typically we're just drawing a very small portion of the curve, so you're not getting that classic up, down, up curve, right? You're not getting the 2 humps. You're just getting a very small portion of that curve between 0 and 12. Any questions about this? All right.